Good morning, students. So now we'll go for the third applications of variational principle. So this is the third application. Application is nothing but simple harmonic oscillator. Of course, we know the equation for the simple harmonic oscillator is given by kinetic energy or potential energy. The very important thing is that the potential energy varies with x square. Okay, so this is symmetry about its mean position, x square. So the trial wave function that we are going to choose to obtain the variation method to minimum energy, it should be also e power minus alpha x squared. Very, very important one. So earlier we had seen two problems. This is about hydrogen atom and this is about helium atom, and we chose the wave function e power minus alpha. Okay, now e power minus alpha x squared. So this is symmetry about its mean position, because the potential energy also symmetry. So that's why the choosing wave function for the variation method is very, very important. How we are going to choose the wave function for the particular system, that accounts. Okay, so we are going to choose this wave function. We are going to prove the energy. We are going to get the energy. Okay, that's our idea. So we have chosen the wave function psi of x equal to a e power minus alpha x squared, and of course as usual we'll have to calculate with normalization constant. So a squared psi star or psi dx equal to 1. So this is one dimensional problem, simple one. So that's with respect to dx, with respect to x. So your psi will be this one. So psi star will be psi star multiplied by psi will be e power minus 2 alpha x squared dx. It's a Gaussian function. Okay. So normalization constant. So e power minus alpha x, of course this is minus into plus infinity. So in the earlier case it was 0 to infinity. At the time we used gamma integral, but this time we are going to use some standard integrals which are nothing but given by this. So e power minus ax squared dx is given by this integral. One dx is missing here. Okay, x squared e power minus ax squared dx, which is equal to 1 by 2 root of pi by a cube. Okay, so this integral we are going to use. So you have now a squared root pi by 2 alpha, which is equal to 1. We have used e power minus ax squared. Answer will be root pi by a. Correct. E power minus ax squared dx will be root pi by a. But here we have 2 alpha x. So answer will be your 2 alpha. So pi by 2 alpha. The answer will be root pi by 2 alpha, which is equal to 1. So a squared will be root of 2 alpha by pi, and a will be root of alpha to the power 1 by 4. Okay, here also there's a mistake. 2 alpha by pi to the power 1 by 4. So that's a mistake here. A equals 2 alpha by pi to the power 1 by 4. So your psi will be a e power minus alpha x squared. Your a will be this one. We have found out. So complete wave function we have found out. Next we are going to find out kinetic energy and potential energy. Substitute. Okay, that you will have to use variation method. So this one, expectation value of h divided by your this one, normalization constant. So that will be a complete wave function. Correct. So this is what we know already. Complete energy. So your expectation of h is given by your kinetic energy. Kinetic energy is nothing but total energy is nothing but kinetic energy plus potential energy. So we can calculate now individually. First we will go for kinetic energy. Okay, so minus h bar square divided by 2m d square dx square sandwich between your ket psi and bra psi. Okay, so this one. So we will just take constants out. Okay, this is your psi n which is equal to this one. Just take constants out. This multiplied by with another one. So that will give us 1 by 2. Psi star psi, correct. So you will have to multiply 2 times. So that will give you 2 alpha by pi to the power 1 by 2. Then it is 1 by 4. It is 1 by 2. So this will be your psi star. This will be your d squared by dx squared psi. So you will have to differentiate this one with respect to x 2 times. We will have to differentiate. So differentiating this, that will give you minus 2 alpha x e power minus alpha x. We have differentiated once. You differentiate again. So keeping x as constant, you differentiate this. Keeping this as constant, you differentiate this. You will get this expression. Okay. So you will get 2 alpha by pi to the power 1 by 2 integration minus into plus infinity this term multiplied by this term. you multiply this term here inside. So you will get this expression. So individually we can integrate now. So we have integral using this standard integrals. Using the standard integrals, we can integrate this. So that will give you 2 alpha by pi to the power 1 by 2 minus 2 to alpha you pulled out. So you have now this term, okay, e power minus 2 alpha x squared. So use this one. You will get root pi by 2 pi by a. So here you have pi by root alpha to the power 1 by 2. Is it okay? Root pi by a. So you will get root pi by 2 alpha. Here 2 alpha is there. So it must be 2 alpha. Plus similarly you 4 alpha squared you pull it out. X squared e power minus 2 alpha x squared is given by this one. So 1 by 2 you will have 1 by 2. 1 by 2. All 4 alpha squared already we have pulled out. Multiplied by 1 by 2. So this answer will be pi by 2 alpha whole cube. So you will get 8 alpha cube to the power 1 by 2. Okay. So now 2 gets cancelled. You have 2 alpha squared. Remaining term you can write like this. And here you can simplify as minus 2 alpha here. Bring it here. This term you can write here, and this term you can write it here. Okay. Now this root pi and root pi will get cancelled. 2 alpha to the 1 by 2, 2 alpha to the 1 by 2 will get cancelled. So you have only minus 2 alpha. Very simple. Here you have 2 alpha squared. You just simplify this one, you will get 2 alpha. As usual, root pi will cancel. We have 2 alpha divided by 8 alpha whole cube to the power 1 by 2. So kinetic energy can be simplified by this expression. Okay. Is it okay? So you have minus, this is the same term I have written, and 2 to get cancelled. You have 1 by 4 alpha squared. So minus 2 alpha here, and simplify these two will give you 2 alpha squared divided by 2 alpha. Is it okay? So your these 2 will cancel, this alpha will cancel. You have minus 2 alpha plus alpha, that will give you minus alpha. So total kinetic energy is given by minus alpha. Okay. Your kinetic energy will be minus h bar square divided by 2m d squared by dx squared sandwiched between bracket psi and bra and ket size. And this time already we have calculated as minus alpha. So your minus h bar squared alpha divided by 2m, that will be your kinetic energy. So we have calculated one part, kinetic energy part. Now we will go for the potential energy part, very simpler one. So potential energy part is given by half m omega squared x squared. Now x squared sandwiched between ket psi and bra psi. And of course we know the expression for psi, you substitute here. Okay, substitute, you will get 2 alpha to the power 2 alpha by pi to the power 1 by 2 x squared e power minus 2 alpha x squared. So just use this standard integral, you will get this expression. Okay, so you have 1 by 2, here you have 1 by 2 and 2 alpha is there. So you have instead of a cube you have to write 2 alpha whole cube, that will give you 8 alpha cube to the power 1 by 2 to the power 1 by 2. So the same thing I have written here, 2 to get 2 and 8. So that will give you 1 by 4. So 1 by 2, 1 by 4 alpha square to the power 1 by 2. So that will be 1 by 2, 1 by 2 alpha. So 2 to 4, that will give you 1 by 4 alpha. So your x squared, the answer for x squared will be 1 by 4 alpha. Potential energy is given by half m omega squared x squared. So answer that we have obtained as for x squared 1 by 4 alpha. Simplifying, that will be m omega squared by 8 alpha. So total energy will be kinetic energy plus potential energy. Kinetic energy expression already we have completed, h squared alpha by 2m. Potential energy just now we have calculated m omega squared by 8 alpha. So we have to use variation method. We have to minimize the wave function with respect to alpha, and this will become h bar squared by 2m. Differentiating with respect to alpha, alpha becomes 1. So here you have 1 by alpha is there. So that will be minus 1 by alpha square. Okay, 1 by x will give you minus 1 by x square. So h bar square divided by 2m minus m omega square by 8 alpha square, which is equal to 0. So which is equal to 0 means this expression can be written as exactly like this. Cross multiplying will give you this. We need to have only alpha value. So alpha squared equal to this one. So your alpha will be m omega by 2th class. So we have found out now alpha. Substitute in this expression. That is the idea. You just substitute in this expression. So substituting in this expression, we will have this one. So you have kinetic energy plus potential energy with alpha. Alpha is given by this. You substitute, you will get this. Okay, m will get cancelled. H bar and H bar 1 H bar will get cancelled. 2 2s are 4. So you have H bar omega by 4. Here also simplifying you will have H bar omega by 4. Correct? So m will cancel. 2 1 by 4 you will get. So you will get H bar omega. This omega will cancel. So you have H bar omega by 4. 1 by 4 plus 1 by 4 is 1 by 2. So we can write H bar by 2. 1 by 4 plus 1 by 4 is 1 by 2. So H bar omega by 4 plus H bar omega by 4 is given by H bar omega by 2. Where have we seen earlier this one? H bar omega by 2. We have seen the expression for harmonic oscillator n plus half H bar omega when n equals 0. You will get H bar omega by 2. So this is for the ground state energy. So for the ground state energy n equals 0, we know the expression for harmonic oscillator En equals n plus half H bar omega. When equal to 0, you will have H bar by 2. So ground state energy. So the tail wave function which we have chosen is the correct one, which is the Gaussian wave function. So that's why we are able to get the correct energy H bar by 2. Okay. So variation method is the best method. Which is the best method to find out, especially to find out the ground state energy and also for the first excited state energies. Okay. So that is the end. So thank you students. We will see in the next class.